Hi everyone. Welcome to this Wind Power Engineering webinar, Optical Fiber Applications for Wind Power Systems. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thanks for joining us. Now before we start, just a brief agenda. Before I introduce our speaker, that is, this webinar will be available at windpowerengineering.com, and a link to it and the slides will be emailed to everyone who is registered. And at the end of the presentation, we'll have a brief question and answer period. Of course, not everyone who wanted to be here could be attending today's, so you can help them learn from it by tweeting the key points and the takeaways you think important. In your tweets, be sure to include the hashtag WindWeb. I think you'll see that at the bottom of the screen in the panel to the right. Okay. After the presentation, I'll read the questions that you and the audience have submitted. And you can do that by typing them into the questions box on your GoToMeeting panel. You should see that on the right bottom of your screen. We'll try to answer as many as possible before the hour is up. Okay. Now let me tell you a little bit about our speaker, Eric Kiefer, and then I'll turn the microphone over to him. Eric has an electrical engineering degree from Purdue University, and he is responsible for product marketing for Avago industrial fiber optics products in the Americas. Before that, he spent many years as a field sales engineer supporting customer designs in industrial and data communication network applications. Okay, and with that introduction, Eric, let's begin. The microphone is yours.
Well, thank you, Paul, and appreciate everyone attending today. I'm at the first slide, so why don't we get rolling? Again, the topic of discussion here is related to industrial fiber optics products and how they can support galvanic isolation and noise-free communication in wind power application using fiber optics. So for those of you who aren't aware of Avago Technologies' heritage, we actually date back to the days of Hewlett-Packard Semiconductor Group. We were formed as an internal source and development arm for products that Hewlett-Packard couldn't find on the external market. And as such, we have developed and have access to quite a few patents based on our optical and analog interface component expertise. Very engineering-driven company, and very focused on leveraging our expertise in optics management and microwave and RF semiconductor devices into new and emerging markets. We're headquartered both in San Jose, California, as well as Singapore. My division happens to be headquartered in Regensburg, Germany, and then we also have production facilities in the Far East, China. Specifically as it relates to the industrial fiber optics products group, our history does date back to the very early years of Hewlett-Packard. The first products that we released were roughly in the mid-'80s as part of HP Components. In 2007, we actually acquired the industrial or the plastic fiber optic group of Infineon. It actually offered us a strengthened position in support of the automotive networking, industrial, as well as home networking applications. We actually offer, as part of Avago Industrial Fiber, basically products that support all the different fiber media and link requirements. So we can support plastic optical fiber, hard clad silica, glass fiber across many different link distances. Since we were involved in this business early on with Hewlett-Packard, we have volume manufacturing capabilities set up. That allows us to manage short lead times and support our products for very long-term support. In fact, our initial HP product platforms that were developed in the mid-'80s are still in production today. We feel it very responsible to our industrial customers who we know have long design cycles and long product life cycles that we keep our products alive and active for long periods of time. So I guess the next section is just a few things to kind of say, so why is this of interest to us? Why should we all be here? Why should we be interested? So this slide is a cut from some information from Wind Power America, and it kind of shows there was an initiative or a concept of having 20% of our wind, or of our energy consumption generated by wind by the time 2030 rolls around. So what would this look like, and how are we performing here? Certainly we did have a slight dip in 2010 from an implementation standpoint, but interestingly enough, based on faster adoptions early in this cycle, we're actually ahead. We're at 44 gigawatts of installed capacity for wind power today, and that's ahead of actually the plan. So that's actually pretty good. What it really shows here, though, is we're still early in the game. So the big years, the years where we really need to take advantage of and grow the business, is in the upcoming 10 years. And this is the big reason why we have a lot of interest in our business as well as our customers' business. Similar from the same publication, it kind of shows kind of the change in, I guess you'd say, geometries over the course of time. Certainly what we're seeing is the power that's generated by wind turbine going up and up and up over the years, and thus the geometries, whether that's the blade geometry or the height of the tower, going up year over year over year. Both of these facts play very nicely and heavily into the technologies that we're talking about today. As power goes up, as size goes up, fiber optics communication becomes more and more of a viable and necessary implementation scheme. So the drivers of wind power, why is this of interest, or why is this being implemented more and more? These are from that same publication, and clearly they probably ring true to everything that you've heard of or seen if you've looked at things recently. Wind costs are coming down. However, federal and state policies play heavily into that capability and that progress moving forward. The fuel price uncertainty is something that we all feel at the gas pump every day, and I think that's something that has some legs to it moving forward. From an economic development standpoint, I think that plays not only into our ability to meet the needs of building the equipment, but also, how is the economy doing? How are we able to sustain this developing and growth and investment business in the course of what continues to be somewhat of a struggling economy? And then certainly public support goes back to not only people's interest in becoming somewhat more renewable-centric green power, but also how does that play into people's ability to continue to fund the federal and state investment into making this a viable technology. I think those are the major points that I'd like to talk on. The others also play a role. So how does this transition, or how can we transition nicely into kind of some of the back data that we talked about trends in the market, into how does that play with fiber optic communication? So the key point here that two things I'd like to kind of take away as something to keep in the back of your minds. Fiber optic communications, specifically industrial fiber optic communications values, offer reliable data control and communication, and it's actually offered in such a fashion where the cabling design and assembly is very cost effective. The values that it provides is no crosstalk or immunity to crosstalk because we're communicating over fiber optic cable. We limit the risk and the effects of, say, environmental issues like lightning strikes. And then we offer infinite voltage isolation from one end, the transmitter, to the other end, receiver. In this case, we kind of look like an optocoupler on steroids. So on this slide, I go through the value propositions of fiber optics in general. Some of these apply more heavily weighted, some of them not so much in the application, but they all play a certain role in developing the understanding for what value we provide to our customers. Basically, we provide high electrical isolation or insulation. I mentioned that earlier. We have an LED transmitter, if you look at the bottom picture, on one end, and a receiver distributed some distance away. Can be 1 meter, can be 10 meters, can be 50 meters. But regardless, between those two sources, you have a cable made of plastic or glass that can offer you basically immunity and isolation. The second point is long distance transmission. I don't want to mention that it's only long distance. Certainly that is one of the values of fiber optics in general. For plastic fiber, we can go anywhere from very short meter, less than meters, all the way out to 100 meters or so. And then we have technologies that allow us to go the longer distance. So basically, fiber allows us to do a continuum from very short lengths all the way to very long lengths. As I mentioned earlier, we are immune to EMI. The interesting part about that is that it allows us to possibly, or allows you as an end user, to run our plastic optical fiber or glass optical fiber right next to power lines or power cables in your designs with no risk of crosstalk among channels. That leads to the next point. In order to do that with copper interfaces, and oftentimes it's required that you have extensive shielding on your cable, makes the cable a little bit tougher to manage, a little harder to handle. We don't have that issue. We work in hostile environments. Specifically, we mentioned lightning as one of those. So we can offer the fact that if should a lightning strike occur, and they do, that we can limit the effect on the systems within a wind turbine. So we can't promise that nothing is going to be damaged, but what we can say is we can prevent the coupling of that electricity across board to board to board. It is a high data security communication. So in the case of when you might be networking different towers together, more than likely via glass fiber, it's being done via, again, light. Therefore, the ability to hack in or mess with that communication is limited. You can break the fiber cable, that is true, but again, you can't hack to it. And the last point is lightweight. And I think this is an important thing that that's worth commenting. Plastic optical fiber, and glass for that matter, is a lightweight cabling mechanism. And also for plastic, which we communicate for up in the head end or the nacelle, it's actually very easy to terminate. So in general, this is the value propositions we talk to when we talk about fiber optics. So here's that picture of the lightning struck wind turbines. This kind of just reiterates the fact our value specifically in wind turbines is often the fact that we are immune to EMI. So in these systems, in these large systems and growing larger systems, you have a lot of high power generation, high power management devices that create a lot of noise. So if running plastic optical fiber can prevent that from being coupled throughout the system or creating issues with your control and management circuitry. And then the second point is lightning strikes. So this just gives you a quick idea to the concept of easy termination. This is an example for POF, as it says, key value proposition of POF components. POF for us means plastic optical fiber. So this is for our shorter length distances. Mainly you'd say somewhere in the vicinity of 50 meters, basically down to say 1 meter or so. So the concept to create a plastic optical fiber connectorized cable is basically you just strip back the fiber. You can insert it. This happens to be a crimpless connector. So basically the fiber slides on the ferrule, you clamp it shut, cut it in step 3 in the lower left-hand corner. You cut it to a minimum, roughly a millimeter or so protruding from the polishing assembly, and then you just do a figure 8 on a piece of 600 grit sandpaper. Very quick process, very easy process to do in the field. So again, just to kind of go back to those key talking points we talked about earlier, again, the industrial fiber optics products offer you that reliable data and control communication. It's cost-effective and flexible cable design and assembly. And the end values of these things is galvanic isolation and EMI noise immunity. So how does that play into the actual designs themselves? So talking in the nacelle up at the top, for your power control and management circuitry. So on one side you're going to have the low end, the low power CMOS circuitry that is managing and controlling the high power IGBT products in the power circuitry. What we find is many cases people run plastic optical fiber from the low power control circuitry and monitoring circuitry up to the IGBT and power circuitry, whether that's in the inverter block or in the rectifier block. And again, that provides you that isolation from your low end, low power circuitry up to your high power circuitry. These links tend to be very short, can be anywhere from 3 to 10 meters. So it's not stressing the fiber optic link at all, and it's actually offering you that value. So these are some applications. The rectifier and inverter, control board that would be mounted on the other end, and the traction control unit. That again, part of this is actually also not only controlling the circuitry that's in the power elements, but also taking the feedback signals back from those building or from those blocks to the control circuitry to make sure we're providing proper control. This just gives you another, I guess, pictorial of the products that might be used for these applications. In the lower left-hand corner, these are the products that were developed in the mid-'80s by Hewlett-Packard. They actually are called Versatile Link, as you can see kind of in the pictures above. They offer control and communication from DC data rates, so very low. You can have very static signals for a long period of time, which is important for a lot of these low-speed control and low-speed feedback signals, up to about 1 megabaud, 5 megabaud, 10 megabaud, and we'll see that we have actually a 50 megabaud device coming out soon. The distances run anywhere from, again, up to about 40 or 50 meters. So in most cases, for these applications, we have more than enough optical power to handle the communication requirements that are out there. Should they need longer distances, you'll see in kind of the lower part of the screen, you'll see HCS come up here. This HCS is hard-clad silica. It's a large core glass fiber, and it allows us to get link distances significantly longer using the same optical products over here. Sorry, clearly I just found my pointer. So this slide is simply intended to show the fact that there are obviously a lot of building blocks, a lot of technologies within the nacelle of a wind turbine. In most cases, these are all going to be required to be monitored and controlled to maintain optimal performance or just determine if there's something going on. Plastic fiber plays a huge role in this as well. So as we go to say a higher level of control, where now we've taken all these inputs from the top of the nacelle, where plastic optical fiber plays a huge part, shorter link distances tend to be lower data rates, where we're now aggregating some of this data to do more system level control and monitoring, we tend to move to some more higher bandwidth products, as you can see here. And longer distance products, as you see here, and maybe more of a migration to a glass fiber optic technology, which is pointed out in this area. So again, we've aggregated, we've taken all these remote and discrete inputs up at the top of the nacelle and managed them up there. And now we may be communicating at a higher level down to the ground or within systems on the ground. So these products here, the HFBR 15, 26, 25, 26 devices, these are used mainly with plastic optical fiber for limited link distances up to 100 meters. This device, the AFBR 5978, is a fast Ethernet transceiver that can be used over plastic optical fiber. And then the components down here at the bottom, the last four, are glass-based technology that have significantly longer link distances attached to them. So we can actually do much more networking of turbine to turbine to turbine. So kind of in a little bit of a conceptual block diagram. So in this area up here, we kind of have the nacelle. And this particular application shows CAN bus as the protocol for managing the feedback signals, the control signals. In that application, in a nacelle, we would communicate or suggest CAN bus be managed via the plastic optical fiber products, the versatile link type devices that go 5, 10, 50 megabaud up to 50 meters. For the higher level networking applications highlighted here in the red, where you're going up and down from the top to the bottom of the tower or tower to tower, they reference Ethernet as a communication protocol. In most cases, that's going to be run, as you can see over to the right here. You can see where this says 62.5 micron. That would tend to be run with glass fiber optics and using some of our either discrete products, which are down here in the lower right-hand corner, or a traditional networking fiber optic transceiver package, which is what this is that I'm pointing to now. So we have products that can fit all the networking, all the control communications within the wind turbine application and wind farm applications. I'm having some challenges advancing the slide. Okay, thank you. Okay, I guess it was just catching up to me. I'm sorry. So we talked about kind of like the discrete, I guess, products by application that the Avago industrial fibered product line fits into. I just wanted to kind of provide a quick highlighted overview of the technologies that are out there. We won't go into a huge amount of detail here, I promise. But on the left-hand side, kind of in the amber color, the more, I guess, greenish or yellowish color for me, is our 650 nanometer products. These devices are the parts that would work over shorter link distances over plastic optical fiber and can be used at the top of a nacelle. To the right, over here in the, I guess I'd call it more goldish color, is our 820 and 1310 nanometer products. These products offer that longer link distances and would tend to run either from top of the nacelle to bottom of the nacelle or within a wind farm for networking purposes. Basically, for the plastic family, we offer discrete devices as well as transceivers. And we'll touch on more on that in a moment. To highlight a little bit further the more networking-based products, in case you're looking or you have the need to do higher bandwidth, higher link distances for networking purposes, I wanted to highlight this slide as well. This is kind of a confluence of both our networking fiber products as well as our industrial fiber networking products, and shows our real strength in the communication area. So for fast Ethernet, we do offer networking products for glass optical fiber. This is all glass. That would support the various IEEE standards of communication, which is over here on the left, whether that be 2 kilometers or 10 kilometers. Similarly, for 1 gigabit Ethernet performance, we offer similar product platforms to meet those needs. And in fact, we offer pluggable modules. That's what SFP is. We offer pluggable modules that can extend your link out to 80 kilometers over single mode fiber. There is a lot of data on this slide. This is all published information that we can gather for you if you have questions, or that you can get from our website. So, what products do we have coming out or recently released that kind of enhance our position now and offering in the alternative energy space? So traditionally, these versatile link products, the ones that kind of have the little jowls on the side of them, actually were only optically spec'd. The optical link parameters themselves were actually historically spec'd to a limitation of 0 to 70. The parts themselves were guaranteed to operate minus 40 to 85, but the optical parameters were only spec'd 0 to 70. So recently, we've upgraded the performance of these devices to actually include full performance, full spec performance over the entire temperature range of the device, as well as reduce the MSL level, so they're a little bit more, I guess, manufacturable friendly. These products are released. These families are anywhere from 1 megabaud to 5 megabaud. This is our 125 megabaud part in that family. Similarly, we just released a fast Ethernet transceiver that can be used over plastic optical fiber for lengths of around 40 meters. Where we see the value of this is we see more and more people looking to embed Ethernet or IP as part of their communication closer and closer to end devices, allowing them to monitor system status via the web. So this device is released now, actually, and it offers 3.3 volt communication. It actually communicates via or directly to industry standard physical layer ICs, a broad industrial temperature range, and it actually leverages the work that was done with Hewlett-Packard back in the 80s with the versatile link connectors. It uses that same connector scheme. For those people who require significant voltage isolation within a single circuit board, traditionally the devices, and I apologize, I'll step back real quick. So these products that we have here have discrete transmitters and discrete receivers. So generally speaking, we're talking about isolation between printed circuit boards, where they're geographically located a meter or more apart. I mentioned earlier that our parts are kind of optocouplers on steroids. This kind of brings the message home true. What we've created here is an optocoupler with a creepage and clearance spec of over 22 millimeters. What that allows us to do is provide 12 kV of isolation, transmitter to receiver, for applications that might require that high level of isolation within a single circuit board. I hope I've explained that okay. It is a DC to 10 megabaud part. That's one of our first products. We do expect to enhance this with future versions. Only through whole components, by the way. It is built off of the versatile link optical family. So what design resources do we have? So we actually offer application notes. This is from our selection guide, which is a very short and to the point selection guide for the industrial fiber products. On the left, as you can see, is our plastic or hard-clad silica products. For each of the product families that are highlighted in this area here, we actually have a various number of app notes that allow you to realize the data rate and link distance that we spec in the selection guide. It actually offers printed circuit board layouts. It offers bill of materials. It offers quite a bit. So it's actually a really good design resource for our customers. Similarly, over to the right-hand side of the page, for the discrete glass products, we offer similar application note support. This is for the 820 and 1310 discrete products. In addition to the technical resources in the form of just app notes, we also offer evaluation platforms for the various products. So basically, all these are kits that we offer that would include the circuit boards you see to the right, but then a length of cable, connectors, the associated materials that you would need or want to build a fiber optic link so that you can actually put it in your system. There, in most cases, are SMA feeds off to the side where you can pump in your electrical data, and then you could run your plastic fiber, whatever, through your system to see if, again, the EMI noise immunity is there, or the isolation is there. This allows you to quickly evaluate if this technology does what you hope it could do. And again, it's available across a good number of our technologies that we offer. Oops. So in summary, I guess, so wind energy, the business and the application direction. I think earlier we mentioned alternative energy, wind energy remains a growing market. It is something that continues to be developed. More installations are happening. More plans are being made, including offshore, which only makes this even more interesting. The size of the masts and the blades continue to increase, which means our power and our efficiency is increasing. And the size and the locations of the farms are getting bigger or getting harder to reach, especially in the case of offshore, which means longer link distances, and that continuous monitoring and continuous performance becomes an even more critical feature. And then lastly, product reliability and system on time remains very critical for these applications. If they're not spinning and creating energy, they're just taking up space. So from a fiber optic standpoint, we mentioned earlier, we offer high electrical isolation, long-distance communication, EMI noise immunity. We work in hostile environments, and we have a lightweight media so that it's easy to transport and install. So when you kind of look at these two, I guess, converging factors, the conclusion to me is that wind energy actually is a very good match for fiber optic technology. For short distance status control and communication, plastic fiber optics up and in the seal, and then for longer distance systems and control networking, glass fiber optics, whether that's networking from turbine to turbine or whether that's networking up and down the mast. It seems like we're headed in a direction where only more fiber makes more sense. So that's me, I guess.
Okay, thank you very much, Eric. Well, good presentation. As an old weatherman, and a lot of these turbines work out in the hinterland where there's a lot of thunderstorms. So I think a turbine has to function properly in the middle of a lightning strike. So I think the fiber has a strong history or a positive outlook. Okay. Well, let's get to some questions. Okay. There are a number here that remind you viewers that you can type your questions into the box at the lower right of the screen. But I'll start with some of that are already here. Eric, is fiber optic technology currently implemented in wind turbine applications?
Most certainly. The actual versatile link family that I talked about much earlier, the parts with the jowls on the side, as I like to call them, have significant design presence in mainly the higher, 1 megawatt and higher wind turbine applications for those status monitoring and control. We actually also sell the glass products, the parts that are singular for a lot of applications where we're running up and down the mast.
Excellent. Okay. You'll have to do a little interpretation here, but the question reads, how does fiber correspond to the size of the turbine?
I think, if I understand that correctly, I may have just answered that a little bit. So generally speaking, at the top for a lot of the control and feedback signals, we kind of see that point where fiber kind of makes the most sense happening at 1.5 megawatt and larger turbines. That's where the powers goes up, and that's where we've seen more of our products being used in that application.
Okay, very good. Here's another one. For Ethernet connections, can the Avago plastic fiber transceiver provide a drop-in alternative for a copper RJ45 solution?
Yeah, unfortunately or I shouldn't say the presentation kind of makes it look that way. The part was sized such that it would be similar in geometry, but the fact is that fiber optic communication, or the electrical side of the fiber optic link, is different than copper. So you would actually have to have an Ethernet PHY that supports 100 base FX communication protocols. And by the way, there are many of them in the industry based on a lot of the data center products that have been developed historically.
Okay, very good. Here's sort of a comment from a reader. Now, we'll have to figure out how to answer this. But he says, I'd be very interested to learn more about the lightning damage case studies. It's not really a question, but just maybe a request for more information. But here's a question. What percentage of wind farms have T1 fiber access today, offshore versus onshore? And what are the projections for 5 years out? So the first part of that question again was, what percentage of wind farms have T1 fiber access today, offshore versus onshore?
Boy, I would have to research that one a little bit. I don't know the percentage numbers on that. I would be glad to take that as something that if I know who asked it, I will get back. What we do see, I guess, today is much more of a today, and I think that's important to say today. That a lot of the stuff is managed more or less kind of on site, if you will. So we see most of our products involved today on site, where they're running, to a shed, for lack of a better term, locally. We do see more and more that people are going to be going to an Ethernet connection where they can do it remotely, but I don't know the percentages. Clearly, offshore, there really is no. I mean, we have. I think the Nantucket Sound was just approved, so we really don't have much in the way of, other than maybe some experimental type stuff installed. So I think it's a little too early to say what the offshore is going to be, but clearly that's going to have to be something that's remotely monitored, because you can't. There's just no way you're going to put somebody in a, either floating in a boat or out there on these pucks, if you will, in the ocean.
Okay, very good. Okay, another question here. Have you considered the extra cost of adding a multi-channel fiber optic rotary joint for data transmissions?
Channel rotary joint.
Fiber optic rotary joint. Is there such a thing?
So I think what might be referenced now is maybe from the actual nose where the blades are, where it's rotating.
Maybe so. Yeah. Yeah.
Mm-hmm. So have we considered? We have not considered that. That's actually an interesting challenge where we've had some people ask about the ability to do so. The difficult part is, fiber optics does like optical alignment in order to be able to maintain continuous data communication. So the tough part is, how do you maintain that flow of photons predictably as the actual nose would be turning? It's something that we have seen happen in the actual medical industry. People are doing it for some of like the MRIs or CAT scans where there's a rotating media. We don't have anything in production today.
Okay.
But it is something that we could be a light source to support.
That's an interesting product, an fiber optic version of the slip ring. So.
Exactly. Yeah, we actually saw that historically for actually automotive applications for the steering wheel.
Mm-hmm. Ah, interesting. Okay. Oh, here's another question. How is fiber optic being used in sensing applications in wind turbines?
That's a product actually that is being researched for us and by us at this point in time. We don't have an active product right now that's in production, but what could it be used for? So plastic or fiber optics, actually the cable itself has different transmission characteristics if you flex it or not flex it. So one of the concepts is that you could actually determine how the blade is flexing or not by basically sending out an optical signal and seeing what return signal you get back, because you would actually attenuate the signal differently if it's flexing differently. Mm-hmm. That's something we're looking into, not something that I have the ability to share in a broad form. It's something that, if there's interest, we have people in Regensburg, Germany, actually looking into it. But that's how it would be used. I assume that that's what the question would be related to.
Mm-hmm. Okay. All right, here's a little longer question. What's the difference between the single and multi-mode fiber cables from operation reliability, efficiency, and performance point of view? Okay. What's the difference between the single and multi-mode fiber cables from an operations reliability, efficiency, and performance point of view? Can you comment on that?
Okay. So generally, let me, I guess, start out with, generally people talk multi-mode fiber and single-mode fiber only when it relates to glass. In most definitions, all plastic optical fiber is multi-mode, okay? So single-mode fiber versus multi-mode fiber, it actually is related to how the media is created. And for in the case of glass, for example, multi-mode glass fiber is larger core fiber. It's 62 micron. Single-mode glass fiber is 9-micron. So the actual optics involved in working with those different core fibers actually is more expensive in single-mode. What it buys you is it buys you the ability to communicate a much longer distance, because what you're doing is creating a very, very tightly collimated light that's going down that fiber. One of the issues that happens with fiber optics is that over the course of a link, you actually, if you can imagine, different light beams are traveling different distances, if that makes any sense. So one might bounce 10 times, one might bounce 3. The one that bounces 10 times takes longer. And so what you get, what is a nice square electrical wave coming in over longer distances, starts to get rounded out a little bit. And so what you can fix with going to different core fibers is actually you can square that up and get longer distance communication. Does that make sense? I hope I answered the question.
Yeah,
so from a reliability standpoint, the easiest fiber to handle is plastic, because it's big. It's very big. It's 1 millimeter core fiber. You can cut it with a pair of shears. You can cut it with a cigar cutter and connectorize it very easily. Glass fiber, 62.5 micron, which is multimode, is a little harder to handle because, again, it's a much smaller core. Glass is more fragile than plastic. And then similarly, 9-micron fiber is actually the most difficult because it's got the smallest core. They're all very reliable. And the thing about it is, because glass is used heavily in the data communication and telecommunications business, there's a lot of connectorized cable suppliers out there. What was the other question?
In reference to single and multi-mode fiber cables, you mentioned reliability and say something about efficiency and performance point of view.
So efficiency is directly tied to, so glass fiber optic cable actually has various what they call windows of performance, where specific wavelengths of light travel very nicely down different media. For glass, actually, the windows, if you'll look at our parts, you notice I said 820 nanometers and 1310. There are very nice windows of glass transmission of light at those windows. Even better is 1550, which is what they use for long-distance telecommunications. So at these windows, and as you step up from 820 to 1310 to 1550, you get more and more efficiency in how the light is carried. For plastic optical fiber, which is the lower-end stuff, easy to terminate, there is a nice window at actually 650 nanometers, and that's precisely why we have our products slated there. And by the way, 650 nanometers for plastic is actually visible red light, which means for an installer, they can actually determine if they've got a live link by simply looking down the cable, which can actually make it very easy and useful in the install process.
Oh, very good.
And it's eye safe.
Okay, yeah, good. Let's move on to another question. Here, this is a question I can answer. The gentleman asks, any chance we can get a copy of this presentation? And yes, you will. It'll be mailed out to everyone who registered for it. And let's see. Next question is, what are the performances, degradation, and life expectancy of fiber-based transmission system over 20 years?
Well, I mean, so fiber optic products, well, for our industrial products, we've had parts installed in the field for probably that long based on the Versatile Link product family already. LEDs have a performance. They do degrade over the life of performance and operation. That being said, we actually have app notes that show how to effectively and efficiently design using optical budget parameters to create a successful link over the long lifetime of your equipment. So if you were to, the way fiber optic links are designed, and it actually is really, really good, we spec a minimum light output and a minimum receiver sensitivity. We know the maximum cable loss, and we throw in basically a design factor of additional 3 dB of power. And so we give you the worst transmitter with the worst receiver, with the worst cable and a design margin. And if we design to that, we feel very comfortable that people can get a useful link that goes 20 years and beyond.
Excellent.
But it does take some design consideration up front.
Okay. All right. Another question here, just a couple more. Do you also provide turnkey fiber optical solutions in the nacelle, tower down, as well as in the wind parks?
So we are an active optics company. I mean, generally speaking, Avago Technologies, if you look at our website, we work with light. So what we really try and sell is those discrete components that you saw kind of in the presentation. We actually do sell plastic optical fiber with that Versatile Link connector, and it's mainly to enable customers who want to use this HP connector, which is what the Versatile Link is. So we do sell plastic. We sell it with Versatile Link connectors, and we sell it with bare fiber. However, we do not sell glass fiber. Those use industry standard like ST connectors, and ST connectors are basically used quite a bit still in the telecommunications and data communications industry, so there are plenty of cable suppliers that would be out there that could do that.
Okay. All right, one more question. Is there a minimum link distance required for the fiber optic products to avoid saturation of the receiver?
In most cases, no. Generally speaking, when you look at the data sheets, you will see that even in the case of our networking products, no matter how impractical it may sound, normally that received power is at or above the level that the transmitter can provide. So no. I mean, I guess would be the best answer.
Okay. All right. All right, ladies and gentlemen, we are out of time and questions. I want to thank you once again for attending the webcast. You can review it if you wish on windpowerengineering.com, and you can also tweet with us at windpower_engineering. We're on Facebook as well, and LinkedIn. You can discuss this presentation on Engineering Exchange. So this concludes our presentation. I want to thank everyone for their attention. From the staff here at Windpower Engineering, we wish you a good and productive afternoon.